So here we're talking about solving systems using graphs and tables. So a system of equations is a set of two or more equations with two or more variables. A linear system consists of linear equations. The solution of a system is a set of values for the variables that make all the equations true. And so in Algebra 1, you learned how to solve systems using graphing, substitution, and elimination. Today we're going to look at graphing and using the table. Here we want to solve by graphing. We're going to do this by hand. If you know how to use your graphing calculator to solve this, feel free. But for this one, we want to solve this by hand. So the first thing we need to do is rewrite our equations. By that I mean getting y by itself. So in the first equation, I'd have to move the 3x over. So it becomes 2y equals 3x plus 8. Then I divide by 2, so y equals 3 over 2x plus 4. Let's go ahead and graph this first line. So we're going to start with a y-intercept of 4. We're going to go up 3, right 2. Up 3, right 2. Then we go backwards to get the rest of our points until we have enough for our line. Now we're going to do the same thing with the second equation. We have to solve this for y in order to be able to graph it, get it in slope-intercept form. So we've got 2y equals negative x minus 8, because we have to move the x over. Divide by 2. Y equals a negative 1/2 x minus 4. So this time we're going to start at negative 4. Apply our slope down 1, right 2. And in this case, the point of intersection represents our solution. So in this case, our solution is the point negative 4, negative 2. This time we want to solve the same problem using a table. Remember, these are the same equations we just saw, so we can go ahead and rewrite these. This one should be y equals 3 over 2x plus 4. This one is the y equals negative 1/2 x minus 4. And so when we say solve by tables, you could go in and plug in your x and y values consistently, or you can use your calculator to help you out. And you can do that by plotting both of these lines on the y equals screen and then looking at your table. So I'm going to do that off screen. Then I'll put in some values here so you can understand where you're finding these values in the table. So if you plug these two equations into your graphing calculator on the y1, y2 lines and then go second graph, it'll take you to the table of values. Scrolling through the table of values, you will notice that as you scroll through the variety of x values, you're going to look for a point where the y1 value and the y2 value are the same. So in this case, at negative 4, both of these equations have a y value of negative 2. So your solution here is negative 4, negative 2. Here we're going to solve by graph or table. I'm going to choose graph. The table is nice. You can use a graphing calculator or you can do your table of values. I'm going to use a graph because I prefer to graph. So I'm going to graph these by hand. If you know how to graph with the graphing calculator, you can use that as well. I'm not going to do it in this video, but you can always go back and graph this by hand or graph this using your graphing calculator. I'll add to your notes, I'll have a video of how to do that if you don't remember from Algebra 1. But in order to graph these, we need to write them in slope-intercept form. So this equation is going to become y equals 1/2 x minus 2. So we're going to go ahead and graph this. We start at negative 2. We're going to go up 1 over 2. And we've got our line. Then we do the same thing with the second one. We're going to go ahead and put this in slope-intercept form, meaning move the x. So y equals negative 3x plus 5. So we start at 5. We're going to go down 3, right 1, down 3, right 1, down 3, right 1, until we have enough points. And this point, we see our intersection takes place at 2, negative 1, so that is our solution. Here we're looking at linear regression, and what we're trying to get across is we learned in, I think, section 2.5 how to conduct linear regression or line of best fits or trend lines using your graphing calculator. We can use trend lines or line of best fits or linear regressions or linear regression models to create equations of lines and then find their intersection. So we're going to use the graphing calculator to find these equations and then look for their intersection either by hand or probably with the graphing calculator. And so this is just an example of how we would do that. And so they're going to walk us through this example, just a refresher on how to create your line of best fit or linear regression equations. In this case, they're going to calculate both equations, one for New York and one for Los Angeles in terms of this problem. And they're going to do so at the same time using line 1, line 2, and then line 3 to represent your other y values. So here, if you want to practice creating your linear regressions, go ahead and see if you can create an equation for both of these, and then we'll talk about figuring out when were the populations of these regions equal. Here we're going to talk about classifying a system of two linear equations by the number of solutions. A consistent system has at least one solution. An inconsistent system has no solutions. When you have a consistent system where you have one solution, you can have an independent system where it has one solution, or a dependent system where it has infinitely many solutions. So you have some options here. Either you're going to have a consistent system where there's some solution that exists, and it could be independent where it's a single solution, or dependent where it's infinitely many. Inconsistent systems have no solutions. And so if you remember back to Algebra 1, a consistent system, you might see something where there are lines that never cross because they're parallel, an inconsistent system with no solutions would be parallel lines because they'd never cross. A consistent system could be lines that intersect at one spot, or it could be the same line twice where they overlap and they lay on top of each other, intersecting at infinitely many points. Here we want to classify a system without graphing. We want to know if it's independent, dependent, or inconsistent. To do this, we need to compare the slopes and the intercepts. So we're going to write both of these in slope-intercept form. So let's rewrite this one. So that means move the x over. So that's 4y equals 2x plus 6 divided by 4. Y equals 1/2 x plus 3 over 2. Then we'll do the same thing with the other equation so we can compare. So we've got to move, we just got to get rid of the 8 on the y. So we've got y equals 1/2 x minus 3 over 2. So if we look carefully here, this is our first line, this is our second. What we should notice is that these two lines have the same slope and different intercepts. So that means they're parallel. And since they're parallel, they're going to be inconsistent. We can do the same thing for question B. We're going to rewrite this, so we got to get y by itself. That means adding 3x over. So y equals 3x plus 4. The other equation, we've got to get y by itself, so we've got actually a little bit more work to do here. We've got negative 1/3 y equals negative x because we subtracted it, plus 1. Then to get rid of the negative 1/3, we can multiply by the reciprocal. So it'll be we'll multiply by the reciprocal, so negative 3. So we've got y equals 3x minus 3. Once again, we should see that we have the same slope, but different y-intercepts. So these are also parallel. So this is inconsistent. Here we have two more examples. We're going to test if they're inconsistent or consistent. So we're going to go ahead and take a look at this, and we're going to go ahead and rewrite the equations. So first one, we've got to get into slope-intercept form. We'll move the x over, so we'll subtract it. So we've got 3y equals negative 2x plus 1 divided by 3. y equals negative 2/3 x plus 1/3. So here's our equation. Now we want to do the same thing for the other one. We just got to get the 4x to the other side, so we subtract it. So y equals negative 4x minus 3. Notice in this case that we have different slopes and different y-intercepts. So these are two different lines. Since these are two different lines, they're going to intersect. This is going to be consistent, and because they're going to intersect at one point. So this is going to be independent. All right, last one here. We've got y equals 2x minus 3 already ready for us. That's good. But this one needs to be rewritten into slope-intercept form. To do that, we'll start by subtracting the 6x. So negative 3y equals negative 6x plus 9. Divide by negative 3. And so y equals 2x minus 3. And if we're paying close attention here, we should notice something. These are the same line, same equation. All right, so these are not parallel, but instead they are the same line twice. So they're going to lay on top of each other forever. So they're going to intersect an infinite number of times. So this is not inconsistent, it's consistent, but it's going to be considered dependent because it has an infinite number of solutions.